Your final examination will be based on all lectures, right? So from the midterm examination, you have seen that we have checked your knowledge on modulation, especially for QPSK modulation process. And also it tested your knowledge for PCM calculations, pulse code modulation. So that kind of questions will not be there in the final exam paper because it's already tested. But there can be small theoretical questions, very simple questions based on these lessons like modulation and pulse code modulation. And also in midterm paper, you know that MCQs, multiple choice questions were based on theory, and as well as there were small calculations to find out phase and frequency. So phase calculations, frequency calculations, those things can it will be not tested in here because in the final exam we have some lessons comes after the midterm. But when you especially like when you do the first question also that we have bandwidth calculation. So bandwidth calculation was discussed even before the midterm on how to calculate this bandwidth and as well as how to identify a low pass signal and band pass signal. So those things were discussed before the midterm as well, but those type of questions can be tested even in here with regarding calculations or maybe theoretical questions, very small questions. As you can see, the first question is mainly focused on multiplexing. So definitely there will be a multiplexing question either from frequency division multiplexing or time division multiplexing. But overall, what I can say is you need all lessons. So we can't say that exactly you'll be getting from these lessons. It's not actually after the midterm, right? You'll be getting questions from whole syllabus, right? Whole module. And especially the final question will be based on lab assessments or whatever the lab activities that we have done. And also it will be based on wide area network assignment work, right? So we have given you some references, and in the morning we did lecture regarding WAN. And you'll be facing for the class test on Monday. So make sure that you prepare for this WAN module as well, WAN topic as well, because it will be asked in the final exam. So you can see the same format will be asked. In last few semesters, we had only online based examinations for the final exam. So this is the last paper-based exam that we have done before online examination. So I'll be using the same format for this final exam as well. Yes, that's, I told you that it has same format. So same format means there will be 4 questions, right? So this exam is going to be a closed examination. So you have to prepare well for this examination since it is closed book. And you'll be having 4 questions, 4 major questions from the final exam. And it will be just 2 hours. And you know that this 2 hours means this paper contributes only 50% for your overall mark. So I hope you can remember how assessment criteria works for this module. Continuous assessments got 50%, including your midterm examination, it's 30% work, and assignments, it's 20%. So you have lab assignments, lab activities, so you'll be getting marks, and as well as handbook. So there was a problem regarding the contribution, how much contribute from the handbook. So for the lab sessions, I'll be giving you 8% of contribution, like overall we have 20% for the assignments. So this is how it's going to contribute to our marks. For the lab assessments, it contributes 8%. And for the handbook, it was 3%. The rest of the marks, 9%, goes for WAN class test. So overall, it contributes 20% for your assessments. So that's how this will be evaluated. Handbook, you'll be getting 3% from overall marks. WAN classes, it will be around 9%. And lab assessments, lab submissions, and you did practical lab sessions, it will be worth 8%. So overall, it's 20%. And these are from assessments. And this will be added with your term mark, right? So then you have 50% from these two. And from the final examination, we'll be getting 50%. Right? So for a 50% final examination paper, usually we give only 2-hour papers. So that's why you have 2 hours and 4 questions. So we are not allowed to bring calculators because we don't have much calculations in this paper. Like if you have multiplexing questions, definitely there will be calculations, but calculations are not difficult. It's very simple, right? No need to use logarithms. So I feel like calculators are not necessary. And yeah, that's all your workings can be done in the workbook itself. So then calculations also can be done on the workbook itself, right? Yes, for the WAN assignment, I told you that you can bring one cheat sheet. Cheat sheet, I think you know what is cheat sheet, right? Cheat sheets means like you can bring all the short notes and everything can be written into one A4 sheet, right? Only one A4 sheet. Okay, so you can write on both sides, A4 sheet on both sides. I don't know whether you know about the cheat sheet. So in examinations, when we are allowing for open book exams, usually you can see that we allow them to bring notes, every notes, but in here, I'm not allowing you to bring all the lecture slides or whatever the printouts of the references, but you can bring one A4 sheet, which is where you can write in both sides, whatever the necessary things can be written into your A4 sheet. And you can bring only one A4 sheet with all the short notes regarding WAN lecture, right? WAN lecture means we did WAN lecture and also we have references. You can write anything, right? It's up to you. It's a short note, right? Okay, so and that's how it's open book, right? It's MCQ paper, so it's very easy. So since you had very few references and the lecture, and since you didn't submit a written assignment from WAN class, WAN lecture regarding wide area networks, I was planning to give you open book with one cheat sheet, right? So that's why I'm allowing you to bring this answers, right? For A4, in A4. And you can't share it with your friends, right? So you need to bring your own one, own cheat sheet for your workings, right? Lab allocations will be published to model. I think for DBMS also you'll be getting some lab allocations. So with the same allocations, I'm also going to be staying. So anyway, I will publish your lab allocations to the model. So yeah, we will move to the discussion of paper. We'll start with the first question. So I need the answers as well, right? It's a discussion. Yeah. Tell me the answer for the first question. I think this question has been asked even in your tutorials. Define the goal of multiplexing. What is the goal of multiplexing? Yes, what is the goal of multiplexing? Efficiency. Yes, we can transmit signals more efficiently. Yes, efficiency is the multiplexing goal, right? So we have two methods to bandwidth utilization. Bandwidth utilization can be done either by using multiplexing or spreading spectrum method, right? So we have learned only multiplexing method. Multiplexing method gives you efficiency, right? It's related to bandwidth utilization. Spectrum method are the goals. Spectrum method and with utilization methods, we have two methods. Spreading method, what are the goals? We have two goals in spreading methods. Privacy, yes, and anti-jamming, right? Privacy and anti-jamming, yes, very good. So this question is based on multiplexing. We have tried the benefit or goal of multiplexing, that is efficiency. So next, we have a calculation based on utilizes bandwidth of a signal. Similar type of questions we have discussed before, right? So then we'll see how to do this question as well. So first you have to calculate the bandwidth of the signal. So what they say, it says that if a periodic composite signal is decomposed into 4 sine waves, the mathematical representation of each sine wave will be as follows. So you can see how we are representing these sine waves, right? Each and every sine wave represents with mathematical information. So we don't get direct frequency to calculate the bandwidth. So you have to derive the frequency from these mathematical representations, right? So first thing is you have to derive the frequency from each and every mathematical calculations, and then you can calculate the bandwidth of the signal. Right, so we'll start with the first one. It's first sine wave. When you decompose this composite signal, we have 4 sine waves. First sine wave, we have 5 sine 205t. So 5 sine 205t. So how do we represent usually the representation of mathematical representation for a sine wave is its instant voltage is equals to peak amplitude sine 25 ft. So if there's an offset, we have to add plus theta, right? Now this question is having no offset, right? So we can use this equation, a sine 25t. So when 5 sine 205t, for the first sine wave, we can derive the amplitude. Peak amplitude is 5 volts and 205t. So 205t. We can see 5 will be cancelled. T cancelled. 2F is equals to 200, right? So then 2F is equals to 200, which means frequency is equals to 100 Hertz. Okay. Then we have 5 sine 605t. 5 sine 605t. So peak amplitude is 5 volts. Then 605t, 605t, 5 and t will be cancelled. So then 2F is equals to 600, where frequency is equals to 300 Hertz. And then we have 5 sine 1005t. So this is the third signal. A is equals to 5 volts. So peak amplitude is again 5. 2F is equals to 1000. Frequency is equals to 500 Hertz. And then 5 sine 1400 5t. So again, peak amplitude is 5 volts. 2F is equals to 1400. Frequency is equals to 700 Hertz. So these are the frequencies that we can derive from these mathematical representations. So we have 4 sine waves. So you have to calculate the frequency and find it out, because its frequency is not 200, 600, 1000 and 1400. You need to find the frequency. First thing is you have to know what is this equation, and then identify 2F. 2F is equals to 200 for the initial one. Then you can calculate the frequency as 100 Hertz. From the second sine wave, it's 300 Hertz. Next, we have 500 Hertz, right? And finally, 700 Hertz. Then we can calculate the bandwidth of the signal. Now, when you consider these sine waves, another important part is you need to identify which one is the fundamental frequency, because in the representation of the frequency spectrum, you have to show which one is the fundamental frequency. So in this findings, you can see the first mathematical representation of the sine wave, where you have a frequency of 100 Hertz, work as the fundamental frequency. This is the fundamental frequency. So all of the other sine waves works as their frequencies are harmonic frequencies, right? 300 Hertz, 500 Hertz, 700 Hertz are integer multiples of this fundamental frequency. So fundamental frequency is 100. You can see the second sine wave is 300 Hertz. So it's 3 times the fundamental frequency, right? So this sine wave it is a third harmonic frequency, right? 3 times the fundamental frequency. So this is going to be the third harmonic frequency. And next, 5 sine 1005t, this sine wave will be fifth harmonic frequency, because it's 5 times the fundamental frequency, right? It's 500. So it's 5 into 100, or we can say it's fifth harmonic frequency. And the last one will be the seventh harmonic frequency, because this sine wave is 7 times the fundamental frequency, 7F. So F representing the fundamental frequency. So it is the 7th harmonic frequency. So you need to identify these information in order to represent them on the frequency spectrum diagram, which is in the next question, or part B of the same question. So part 2 of the same question. Okay, so now we'll see how to calculate this bandwidth of the signal. So bandwidth of the signal is based on the highest frequency and the lowest frequency. So from the calculations, we have identified that this is bandwidth of the signal is the different frequencies of the signals are 100 hertz, which is the fundamental frequency, and it was the lowest frequency, and the maximum or highest frequency was 700 hertz. So when you take the difference between highest and the lowest frequencies, we can get the bandwidth of the signal. So it is 600 hertz. So this is how we apply these values and derive the frequencies. And then you can calculate the bandwidth of the signal. It is the difference between the highest frequency and the lowest frequency. So 700 subtracted by 100 hertz. Bandwidth of the signal is 600 hertz. So when you do this type of questions, don't write straight away 700 minus 100 hertz, right? Always write the equation and apply the values. So equation is highest frequency minus lowest frequency. So write that equation first and then write the values. Now we have to represent these frequencies on a frequency spectrum diagram. So in the next part 2 of the same question, it says draw the frequency spectrum of the signal indicating the fundamental frequency and harmonic frequencies. So you have to draw this frequency spectrum. In frequency spectrum, what do we have? We have y-axis with amplitude, x-axis with frequency. In time domain spectrums, you have learned that time domain spectrums have y-axis is amplitude, x-axis is time. So in frequency domain spectrum, instead of time, x-axis replaces with frequency parameter. Now, we can't map these frequencies unless it is a periodic composite signal. Right? So in the question at the beginning, it says it's a periodic composite signal, right? So therefore, we can map these frequencies on a frequency spectrum, and we have discrete values for frequencies, right? In a non-periodic composite signal, we don't have discrete values for the frequency. It will be a continuous frequency variation. So this is how we can represent it on frequency domain spectrum. So all of these sine waves were having same peak amplitude, 5 volts. So all of these representations will have 5 volts of peak amplitude. And you can label these fundamental frequency, third harmonic frequency, fifth harmonic frequency, and seventh harmonic frequency. Now this, I think I have told you this in the lectures as well. Now this is the second sine wave, right? This one is the second sine wave. But do not consider the second sine wave as the second harmonic frequency, because if you consider the fundamental frequency and compare with the second sine wave frequency, you can see fundamental frequency is just 100, right? And second sine wave frequency is 300. So it is 3 times the fundamental. So when you label these harmonic frequencies, always you have to consider the integer multiple of the fundamental frequency, right? How many multiplication, like it's like, now when you consider the second sine wave, if you want to say that this is second harmonic frequency, it has to be 200 hertz, where you have 2f, right? Fundamental frequency multiplied by 2. So then you get 200 hertz. So that can be labeled as second harmonic. This is third harmonic frequency, right? So it's a very common mistake that I have seen in answers of past students. Okay, so now we'll do question number part C. Part C contains several sub-questions. So this question is based on time division multiplexing. It's about time division multiplexing system, right? TDM system. So in the morning also I told you that TDM systems, these levels of TDM systems are having another name, that is digital signal, right? So digital signal 0 means that is the input line which comes from subscribers or individual users. And the primary multiplexer is usually identified as digital signal number 1, right? So that name digital signal is used within this question as well, right? So that's why I reminded you. We'll see the question. A telephone company implements time division multiplexing through a hierarchy of digital signals called digital signal service. A DS level 1 is combined with 24 channels, each of 64 kilobits per second and 8 kilobits per second of overhead, right? So this is a description saying what it is about this digital signal. Here it says digital signal level number 1, which means it's regarding a primary multiplexer, right? Digital signal level number 1 means it's a primary multiplexer. It has 24 channels inputs. 24 channels are digital signal 0, right? DS0. So we are inserting 24 DS0s to our primary multiplexer. Each and every channel worth 64 kilobits per second. So it's important to know how much bit rate, input bit rate sends towards the primary multiplexer. Then 8 kilobits per second of overhead will be added, right? So overhead size is just 8 kilobits per second, and we are adding only 1 overhead. Now, the example that we discussed during the lectures regarding E1 multiplexer, I think you can remember there were 30 channels, right? 30 input channels, each with 64 kilobits per second, and there were 2 overheads. And, overheads bitrate was also 64 kilobits per second, but this one is different from that, right? It has 24 channels, each with 64 kilobits per second, and 8 kilobits per second of overhead, only 1 overhead. Then it says, how do we consider the input unit size, right? Every output slot carries 8 bits. Word interleaving, right? This, if you pass 8 bits in one input unit or one output unit, we call that method as word interleaving, right? Every output slot carries 8 bits word interleaving from each channel, and one extra bit or overhead bit is added to each frame for synchronization. So unit size, input unit size or output unit size is 8 bits, right? They are using word interleaving, right? Not bit interleaving. In bit interleaving, we saw that during the tutorial calculations, we did many questions related to bit interleaving. Bit interleaving, we are using the unit size as 1 bit. But here, this is going to consider 8 bits in one unit slot, right? One input or output unit. Overhead bit, how many overhead bits? Just 1 bit, right? It's only 1 bit. Now we can answer the questions. But when you read this type of question, the first thing is you have to draw the scenario, right? You need to map this scenario. So we are having time domain, time division multiplexer, TDM system. Okay, so this TDM system actually, this TDM system is DS1. DS1 means this is either E1 multiplexer or T1 multiplexer. That is primary multiplexer, right? This is going to be a primary multiplexer. How many input channels we have? We have 24 channels, right? So there are 24 subscribers, 24 channels. Each channel bitrate is 64 kilobits per second. This is the input bitrate. And what else we have? We have an overhead. Overhead size is, bitrate is 8 kilobits per second. And then this will generate a frame where you have 24 output slots, right? So in the first part of this question, you need to draw the frame, right? You need to draw the frame. But here also you can note down how the frame looks like. But actually, when you come to the first part of the question, don't give this as an answer, right? You need to draw a separate frame, including whatever the necessary information, right? So every unit size, like input unit size, let's say that we are passing one input unit. This input unit size is 8 bits, right? On this frame also, one output unit size is also 8 bits, right? Likewise, we have 24 output slots and one overhead, but overhead will pass only 1 bit, right? So this either this first slot or whatever this slot, size worth only 1 bit. For overhead, it's just 1 bit, right? So likewise, we have output slots and one overhead, right? So this is basic diagram. You need this information to do the calculation, right? Now, this is not compulsory to do this diagram. But when you do the calculation, you will make mistakes. Because part 1 question, I have asked you to draw the frame structure, right? You need to draw the frame structure, considering time slot T0 as overhead and other time slots for the channels, 24 channels. So when you draw the diagram, when you draw the frame, if you know how many channels are there inserted to this multiplexer and how much of size for this input unit size or output unit size, and how many overhead bits will be added to this DS1 multiplexer, it would be easy, right? Because you are doing calculations And also you have to draw the frame structure, right? So it's not compulsory to draw this, but if you want, you can draw it. Right. So we'll start with the first diagram, first frame structure. Now, do not include this diagram as the frame structure, right? You have to draw the separate frame structure, right? Right. I'm going to erase this. Draw DS1 frame structure, assuming time slot 0. TS0 is the overhead bit, right? So it's going to be the overhead bit. Time slot 0. So time slot 0 to time slot, how many time slots will be there in the frame structure? How many time slots? Yes, 24 time slots, right? Time slot 0, TS0, and then you have TS1, right? Likewise, you don't need to mark everything because you have all 24 channels. So then the last one is, what is the number? Is it 23 or 24? 23, 24. Some are saying it's 23, some are saying it's 24. So what is the actual number? Now, in the diagram, we saw that we are inserting 24 channels, right? And overhead. Okay, so now actually what I am mapping is this frame structure, right? So time slot 0 goes for overhead, right? Including overhead, how many channels? We have in total 25, right? 25 channels, okay? But remember the size of this overhead is lower than this other channels, right? Channel number 1 to 4, it's contributes 64 kilobits per second and it has 8 bits in one slot. So then if you put this one for the overhead, so you have to mark these things, right? This is the overhead, right? And if this is going to be the channel number 1, this is going to be your 24th channel. So channel number 1 starts with number 1, right? So then the last one is 24. So this is a very common mistake because we have started with number 0, right? So overall, if you count down number of slots in this frame is actually 25 slots, right? But time slot 0 goes for overhead. So then time slot 1 onwards until 24 can place for channel number 1 to 4, 24, right? So last number is 24. If you don't have an overhead, then you can, like in the question, it says which channel starts with, like usually when you don't have an overhead, time slot 0 can be placed as channel number 1, right? Let's assume that we have only 24 channels without an overhead. So then time slot 0 goes for channel number 1. Then time slot 23 will be given for channel number 24 because time slot T0 to TS23, we have 24 slots. So then if you don't have overhead, right? If you don't have an overhead, This goes for channel number 1 and this goes for the last one. So in this drawing, actually you have to note down this TS0, TS1 and TS24. And also you have to mark which one is the overhead and which one is channel number 1 and channel number 24, right? So if you have marked them as well, you will be getting 4 marks, right? So then we'll do the next calculation as well. Next calculation, what is the size of an output frame in bits? So when you read the question, is that how many bits will be there? This is the answer for the first question. Second question. In individual output slot, there are 8 bits. Likewise, we have 24 slots, right? So if you want to take the size of this frame in bits, you need to multiply 24 by 8, right? So that's not enough because we have an overhead. Right? What was the size of the overhead? Overhead is 1 bit. Right? Overhead is just 1 bit. So then, size of the size of an output frame in bits, right? We want to measure how many bits are there in one frame, right? Total number of bits. So if I just mark in one slot, we have 8 bits, right? Because we have 24 bits, 24 slots. And here, overhead is just having 1 bit. So then 24 into 8 plus 1. 24 into 8, it's 192 bits plus 1 bit. So in total, it's 193 bits. So size of the frame is 193 bits. Okay. Then in the part 3, in this question, we calculate the bit rate. Right? In the next question, we need to calculate the bit rate. What is the output bit rate in megabits per second, right? So when you are calculating the output bit rate, always you have to consider how much of input bit rate we have. In the question, you saw that input bit rate was 0 kilobits per second from each and every one, and 8 kilobits per second from the O, right? So then how much of input bit rate will there? How do we calculate it? Yes, number of bits in frame or bit rate. This is how we calculate it. Output bit rate in megabits per second. Now I will reconsider the frame structure. It's not compulsory, but I'll just go back to the design that we sketched because we need to get that benefit as well. Right? I told you to draw this diagram. This one. So if I insert in 24 channels, right? We were inserting 24 channels, and here output frame comes with 24 slots, right? So this was the basic diagram, 64 kilobits per second. And here we have 8 kilobits per second. Okay. So then now we have to calculate the output bit rate. So output bit rate is equals to input bit rate multiplied by number of channels, right? So input, like that is the equation. That's how we can write the equation. But it's not compulsory to write those equations because I think I have told you during the lectures also. We are deriving these equations based on their calculation, right? So we don't have equations to calculate these things, right? So you can consider the output bit rate is equals to input bit rate multiplied by number of channels, right? But we can't calculate the output bit rate from this information only because we have an overhead. So we can't avoid this overhead. You need to add it as well, right? So once you calculate this, you need to add the overhead as well. Right? So then input bit rate is 64 kilobits per second. Each and every channel provides you 64 kilobits per second of input bit rate. And how many channels? We have 24 channels. Plus overhead size is 8 kilobits per second. So in total, 64 into 24, we have 1005. How much? 36 plus 8 kilobits per second. So 1544 kilobits per second. But we have to convert this into megabits per second. So then 1544 multiplied by 10 to the power minus 3. So 1.544 megabits per second. So that is the final answer. So in this type of questions, always show the steps, right? Because if you made mistakes in the final answers, you'll be getting marks for the intermediate steps. Now, for this equation, I'm not giving you marks because it's not a standard equation. But here you're getting 1 mark. If you have written down this step like 60.24 plus 8 kilobits per second. So then we can get an idea that you have identify how to calculate this, right? And you have found this calculation like overall it has 3 marks, right? This question worth 3 marks. So then if you have found how many kilobits per second, or if you have apply this equation, like try to find out the megabits per second by multiplying 10 to the power minus 3, like one of these steps will get 1 mark. And final answer, it's 1 mark, right? So I will be getting marks. Because in the midterm also, I saw that most of you have skipped intermediate steps to derive the final answer. It's better you can do without even calculating all of these things, but it's actually you need to show what are the intermediate steps. So otherwise it will be like if you just write 1.544 as the final answer, it's like you have copied from another person, right? Okay, so we'll move to the next question. We calculate the duration of the frame. What is the duration of an output frame in microseconds? So during the lecture's tutorial discussion, I've told you how to calculate this duration of an output frame, either in microseconds or in seconds. So we have 2 methods, right? Basically, we have 2 methods, like we can analyze the question and figure out how much of duration will be there to transfer one output slot. And then we can find out how much time it takes to transfer 1 bit. Likewise, we can calculate the duration. Or else we can apply the equation like dividing number of bits in the frame by bit rate, right? So when we consider this answer, we can see this total frame size is 193 bits, right? This total frame size is 193 bits. So we can transfer this frame at a rate of 1.544 megabits per second. So that's the bit rate, right? This is the bit rate, how much of speed. So at once, at a second, during 1 second time period, we can transfer around 1,544 kilobits per second, right? So we are transmitting just 193 bits in one single frame. So we want to find out how much of duration is there to transfer 1 bit, right? Just to transfer 1 bit, how much time it takes. If you take 1 second to transfer 1,544 into 10 to the power 3 bits, how much time it takes to transfer 193 bits? Right? So how do we calculate it? So question number 4. Duration of an output frame is equals to number of bits in the frame, total number of bits in one single frame divided by output bit rate. So this is not the only method to find out how much of duration is there, right? I will do only this method, right? We have 193 bits in one single frame, and one single frame can be transmitted at rate of 1544 into 10 to the power 3 bits per second. So bits will be cancelled, right? So when you divide it, the answer is 0.125 into 10 to the power minus 3, right? When you divide 193 by 1544, answer is 0.125. And when you take 10 to the power 3 to the top, it will be 10 to the power minus 3 seconds. So you have to provide answers in microseconds. You need to convert this into microseconds. Converting seconds into microseconds, multiply by 10 to the power 6. So this will be cancelled, right? It's 10 to the power 3. So when you multiply 0.125 by 1000, it will be 125 microseconds. So that's the duration of the output frame. Okay, right. So we'll do the last question from this question number 1, part C. Question number part C, last question, right? 5th one. The telephone company implemented a DS2 by multiplexing 4 DS1 channels plus 136 kilobits per second of overhead. Sketch the TDM system of DS2 and calculate the data rate in Mbps, megabits per second. Now, when you consider this question, if you have sketched the previous diagram, now you can have an idea, better idea with this, right? Now, we sketch this basic diagram with digital signal DS1, right? Digital signal 1. So digital signal was inserted with digital signal 0, right? 24 digital signal zeros, DS zeros, right? 1, 2, up to 24. And there was one overhead. So this basic information was used in the previous calculations, right? And then it was generating output frame. Now what it says now, this telephone company is going to implement DS2. So DS2 means that is a second order marks, right? DS1 is the primary order, primary marks. And next you have second order marks, DS2. So how do we form a DS2? DS2 is inserted with a data rate of 1.544 megabits per second, right? So it says this telephone company implemented DS2 by multiplexing 4 DS1 channels. So that means DS2 is inserted with 4 inputs. And inputs comes from DS1, right? DS1. Four DS1s will be inserted. Individual DS1 or primary multiplexers output bit rate is 1.544 megabits per second, right? So likewise, every DS1 will provide you 1.544 megabits per second data rate to this DS2. Then what else we have? 136 kilobits per second of overhead. There's an overhead. Its size is 136 kilobits per second. Now what we have to do? We need to draw this sketch, or we need to draw this DS2 diagram, and also we need to calculate the data rate in here, right? So we were working with this DS1 before, right? It was inserted with 64 kilobits per second channels. So there were 24 channels, and then we had overhead bits. So it was giving output bit rate of 1.544 megabits per second. Now we are going to combine 4 primary multiplexers and build one second order marks, which is known as DS2. DS2 is inserted with an overhead of 136 kilobits per second. And then we have to calculate the output bit rate, right? So in this diagram, like when you draw the sketch, we don't need to draw this part, right? No need to draw this part. You need to draw this section, which I'm going to square with the red color one, right? This is what necessary for this sketching, right? You can sketch this part to show the TDM system built upon DS2. Next thing is you need to show the calculation, right? How do we calculate the data rate? Data rate or output rate. We are inserting 4 DS1s. So then individual DS1s are contributing 1.544 megabits per second, right? From each and every individual DS1, it's inserting 1.544 of megabits per second rate. Then we have to add this overhead. How much of overhead? It's 136 kilobits per second, right? So data rate is equals to 1.544 into 4. So this is in megabits per second, right? But this one is in kilobits per second. So if you calculate the answers in megabits per second, you have to convert this into megabits per second, right? So converting this into megabits per second, 136 should be divided by 1000, right? So then you can add 0.136 megabits per second. So in total, how much? 6.312 megabits per second. Very good. 6.312 megabits per second. So that is the data rate of DS2. So you need to sketch this squared diagram, right? So this diagram is going to show you how DS2 is generated or implemented, and then the calculation data rate. So next question is actually theoretical questions, the theory-based questions asking from lecture number 5, 6, 7, and 8. Okay, we'll move to the next question. So can you give me answers for these questions? So these are the previous questions, marking guide, right? Marking guide for the previous questions. Calculation of output bit rate, and for this duration calculation, I was giving only 2 marks for this step, right? So these steps are not necessary. You can include them if you want, but these two are the most important calculation steps. So if you write this step, I was giving 2 marks, and this one, it's final calculation, it's 2 marks. And this is the diagram for the DS2. So overall marks is it's just 5 marks. So these things can be different from the marks that you have allocated for these new questions, right? For an example, if there's a question like this, if I'm giving you around 6 marks or 7 marks, then the contributions will be different, right? But for this calculation, it's just 5 marks. So you'll be getting 3 marks for the diagram, and for the calculation, just 2 marks. Okay, so move to the next question. Question number 2, part A. What is local area network? I check the definition of local area networks. You can find is explaining computer network which is designed for a limited geographic area. So it has a group of computers which is connected in a close proximity. So the best definition is to say by including the geographical size as well, because as I told you in the morning, these types of networks like personal area network, local area network, metropolitan area network, wide area network, it's based on the geographical area, right? Size of the geographical area, how it managed. So this explanation you can write a computer network that is designed for a limited geographic area. So that's the definition given in a lecture slide. So what are the benefits? What are the benefits you get from these local area networks? Yes, what are the benefits? We can share files and resources. Very good. Yes, we can share resources. We can share software, hardware, and files. Yes. Centralized data or centralized administration control, right? Centralized administration control, because this is owned by one owner, right? Local area networks are owned by one owner. So we can have faster communication, right? As well as central administrative control. That means in order to make changes, and also if you want to monitor the network, updating, troubleshooting will be maintained by one central administration. So other than that, it's faster communication. It provides you very faster point-to-point communication within the network. And finally, reducing cost, right? It will reduce the cost. So these are the answers for first two questions. So these answers I have taken from the lecture slide, right? Same as the lecture slide. Yes. Part C of this question number 2. There you have a table, right? So when you write answers, if you get a table like this, you have to copy that table into your workbook, right? You'll be provided with a workbook. So in the workbook, you have to copy this answer script, this table, right? Table 1. So what it says, compare the following network devices using the format given in the table, right? So in this table, what are the devices that we are going to compare? Bridge and layer 2 switch. So can you tell me in which layer this bridge operates? Yes, what is the layer that it operates? Layer number 2 or data link layer, right? Layer number 2 or data link layer. This operates in data link layer. Or layer 2. So layer 2 switches, obviously it says that which layer it belongs to. It belongs to layer 2. So you can write data link layer or layer 2. How many collision domains in bridge? Number of collision domains in bridge. So how do we find the number of collision domains in this bridge? In the question, it says bridge is having 2 ports. So that means if we consider a bridge, now this is the diagram for a bridge. This bridge is having 2 connections, 2 segments, right? 2 ports means 2 segments. Each and every segment will consider as 1 collision domain, right? So here, this is the segment number 1, segment number 2. Right? Segment number 2, segment number 1 and 2. So one segment will be considered as one collision domain. So likewise, we have two collision domains. So this layer 2 switch will have 24 ports, right? Layer 2 switch. This is how we draw a switch, layer 2 switch. It has 24 ports. So individual connection, individual port will work as a separate collision domain with switches, because switches are intelligent devices than bridges and other devices, right? So switch will consider each and every individual segment as a separate collision domain. So then we have 24 collision domains. So this is going to be one segment, right? Segment number 1, segment number 2. Likewise, there are 24 ports or 24 segments. So number of broadcasting domains per bridge. How many broadcasting domains? Only one broadcasting domain, right? We have only one broadcasting domain for bridge, and also for layer 2 switches, we have only one broadcasting domain. There's a question. All devices, we have one broadcasting domain. Yes, for all devices, we have one broadcasting domain. Now, for an example, hubs, there's only one broadcasting domain. Bridges, it's same. Switches, it's also same. But when you consider routers, we don't have broadcasting domains. Routers are not doing broadcasting. So they don't count down as a broadcasting domain. Okay. So now we'll check question number part D. So there are sub questions. You need to briefly explain the following problems. So these problems are actually considered as transmission impairments in fiber optics, right? So you have to explain them, as well as you need to draw a diagram, right? You need to draw a diagram to explain this. So what are the fiber optics problems that we have? Constant radius bending, macro bending loss, right? So there are two bending losses. So there are many number of fiber optic impairments, right? Scattering loss, coupling loss, right? Bending losses, absorption loss, right? Likewise, if you check lecture number 6, there was a section, separate section for problems in fiber optics or transmission impairments in fiber optics. So here you have to explain 3 out of them. So when you consider bending losses, we have 2. One method is constant radius bending or macro bending loss. The other one is microscopic bending losses. So both losses will occur due to the bends in the fiber optic cable, right? So in macro bending losses, at what time we get this macro bending losses? During the installations, right? So when we are installing these fiber optic cables in a network, there can be macro bending losses. So how it looks like. Right? So at the time of installation, the fiber optic cables have bends, right? So if you have a large bend like this, the incident angle will change, right? Incident angle at the bend can be less than the critical angle. So then the signal will be refracted to the second medium, or the signal will be refracted to the rare medium, right? So we are transmitting signal, light pulses through the core, right? And how do we transfer that? We are using total internal reflection method, right? To transfer these light pulses through the core. So in order to achieve total internal reflection, there should be two medium, right? So core is a denser medium, right? Core is having high index of refraction, and core is covered with cladding, right? So cladding is having low index of refraction, or it is a rare medium. So when the incident angle is less than the critical angle, the signal will be refracted to the rare medium, right? So if you want to achieve the total internal reflection, we need to achieve an angle of incident which is greater than the critical angle. So then only it will be reflect back to the same medium. So the bending losses, macro bending loss. The second bending loss, which is microscopic bending loss, occurs due to manufacture faults, right? So there can be small bendings in the core, or either the cladding of the fiber, which is resulted from the manufacturing. So then again, the angle of incident can be changed, and the light rays will refract to the rare medium. Then the final one is coupling losses. Coupling losses occurs again due to the installation problems. So when you are connecting two fiber strands together, there can be problems with the splices, or inside the strands, they have different core. The diameter of the core is different from the other cable, right? Other fiber. So like this, there can be imperfectly alignment. So when you imperfectly align these fibers, when you are connecting multiple number of fibers together to expand the network, there can be coupling losses. So it's again a manufacture fault. It's again installation problem where you have imperfectly aligned connectors. So then the last question of question number 2, part E, with aid of diagrams, differentiate ground wave propagation and line of sight propagation. Give one example for each propagation method. So you have to differentiate ground wave propagation and line of sight propagation. So ground wave propagation, this is the image, right? You need to draw the diagram as well to show how ground wave propagation works, right? And for the line of sight, this is how it shows, right? You have, you should indicate an antenna for ground wave propagation where we transmit in signals or propagate signals in all directions. And for the line of sight, you can draw two antennas facing with each other, because in line of sight, we can find two antennas facing with each other in a straight line, so direct connections. Right. So what is ground wave propagation? In ground wave propagation, we are transmitting low frequency signal and it will travel to the lowest portion of the atmosphere, right? And as you can see, the ground wave propagation in here, it will transmit in all directions, right? So signals will be propagated in all directions from the transmitting antenna. So we will be transmitting low frequency signals. So low frequency signals will travel through the lowest portion of the atmosphere and signals will propagate in all directions, right? The antenna of this ground wave propagation will propagate in all directions. What is the example? AM radios, right? AM radio is the example for the ground wave propagation. Line of sight propagation. There we are using high frequencies, right? Very high frequency. Very high frequency signals will transmitted in between two antennas which are facing with each other, right? What is the example? Where do we use this? Line of sight propagation. Satellite communication method, right? In satellite communication method, we are using line of sight propagation transmission. Even mobile phone networks, we are using the same transmission method, right? In between antennas, okay? So you can find the differences from the lecture slide regarding this ground wave propagation and line of sight propagations. So I've taken these images and all the descriptions, examples from the lecture slides. It's in lecture 6, right? Okay. So now we'll quickly check question number 3. Question number 3, part A. Listing the two sublayers of IEEE Project 802 standard. Yes. Can you tell me what are the two sublayers of IEEE 802 standard? LLC and MAC. So LLC stands for Logical Link Control. MAC stands for Media Access Control. So two sublayers are Media Access Control and Logical Link Control, LLC. So next we have to represent line coding patterns, line coding schemes for these bit pattern. Say bit pattern will be represented for all four types of line coding systems. Okay, so we'll see how to represent these line coding schemes. So line coding scheme should represent 100101000. So we have to represent NRZ encoding, AMI, alternate mark inversion, and differential Manchester encoding, as well as Manchester encoding, right? So in total, you'll be getting 8 marks for this part B question. So this is a bit pattern that we need to represent. So I'll show you how to represent it with NRZ first. So it's 100 10100, right? So you can draw one single diagram for this, or else we can draw separate diagrams. So it's up to you to choose whatever the method, right, you prefer. So NRZ method, that's the usual representation, right? Like for normal digital signal representation. So then 0 voltage will have 0. Here it is 0 and 1. And then 0, 1, 0, and 0. So then we have AMI or alternate mark inversion method. It's a bipolar scheme method. Right. Next we have AMI method. The same binary format, right? With the AMI method, for ones or positive values, we have to go with inversions, right? So positive and negative alternatives, right? So when we have 1 in here, you have to start with a positive voltage, but this is 50% of duty cycle, right? AMI with 50% of duty cycle. So then we can start with high voltage, and during the same bit time, you need to reduce it into 0. 0 voltages will represent as it is with 0 in AMI method. So 0 will represent as it is with 0. Next, we have again 1. So I told you that we have to switch between positive and the negative alternates of voltage level. So this one will represent the negative voltage. Then again 0 as it is, 0 voltage. So the next one, it's switched to positive voltage. And last two binary values, 0, 0. So next, we have to represent differential Manchester encoding. What is the special thing with the differential Manchester encoding? Yes, can you remember what is the special feature in differential Manchester encoding? If next bit is 1, no inversion, right? When the next bit is 0, there's an inversion. When the next bit is 1, no inversion. So in the question, it says, you can see differential Manchester encoding start from high voltage level, right? You have to start from high voltage level. So in here also you have one binary 1. So you can represent with high voltage level, right? You have to start with high voltage level. So it has definitely the 50% of duty cycle. Right? This is the representation like in differential Manchester encoding methods and Manchester encoding methods. Remember, we are moving from positive voltage levels to the negative levels and negatives to the positive levels, right? So we don't come to 0 and end up, like we are moving from positive voltage levels to the negative one and vice versa. So let's say that this end is the positive one, and you can see this line as the 0, right? Represents the 0. So I'm not going to draw that. Then we have 0. Next bit is 0. So when the next bit is 0, there should be a transition or inversion. So you have to change the voltage level and change the voltage into a high value and then come back to negative. Again, we have 0 as the next bit. Again, we can see an inversion. Then we have binary 1. So when we have binary 1 as the next bit, no inversion or no transition. So that means we can continue with the same voltage. And at the middle of the bit, you can change the voltage level. Again, the next bit is 0. So then need to change the voltage level from negative value to positive value. So then we have 1. When you have 1 as the next bit, no transition. So continue with the same voltage level and drop the voltage at the middle of the bit time. And then binary 1 again. So you have to show a sudden transition in here. So last one is also binary 0. So then again, a voltage level will change. So that's differential Manchester method. So when you represent Manchester method, how do we represent? Manchester method. For binary ones, it's low to high. It has a specific pattern. For binary zeros, it's high to low, right? Binary ones, it's low to high. Binary 0 is high to low. So then we have binary 1. Binary 1, it's low to high. Binary 1, it's low to high. Next bit is 0. So this time we don't have this differential Manchester method like transitions. It has a specific pattern, right? It's always binary ones, it's from low to high. For zeros, it's high to low, right? 0, it's high to low. Again, 0, it's high to low. Next bit is 1, so then low to high. Then we have 0, high to low. Again 1, low to high. Again 0, it's high to low. Last bit is again 0, so then high to low. So likewise, you can represent like when you draw these diagrams in the workbook in final exam paper, you can draw them in one diagram, right? So you can sketch them in one single diagram like this. So then it would be easy to have the same alignments, right? Or else you can draw them in separate diagrams, right? But if you try to draw them in separate diagrams, you should show the difference between these places, right? When you have continuous zeros, continuous ones, we can see that it's like just 0 voltage for a long time period, right? So it's not going to show you how it differs, right? So it's better to draw these type of graphs under one line alignments. Now, for an example, like for this AMI diagram, this is where we consider the bit time for binary one, right? And this is the bit time. So bit time should noted with this diagram. So since I've used an Excel sheet, you can see equal bit time will maintain in this graph, right? Okay, so next question is based on CRC technology, CRC method. CRC method is an error handling method, right? It's an error handling method. So how do we represent this error handling method? What is the special thing with error handling in CRC? Can you remember the special things in CRC method? Yes, we can find more than one error, right? In CRC method, we can handle more than one error. So it's not like parity method, because parity checking method, we can find only one bit error. And CRC method is actually a binary division, right? This use modulo 2 arithmetic, right? To do division. Okay, so we'll do this calculation. Yeah, what it says, CRC method is error detection method using data link layer. In first part of the question, it says, if the data to be transmitted is given as 110, 10011, calculate the frame check sequence using the divisor 1010. So this is the data stream that I want to send. It's 110, 10011. And this is my divisor 1010. I need to find out FCS, right? Frame sequence. So here it is, this is the bit stream 100, sorry, 110, 10011. So when you divide it to get the answer, we have to use AND operation. And when you subtract, like to get the remainder, we have to do XOR operation, right? I hope you can remember that. So I'm going to divide this number by 1010. So when you consider the first two binary values, it's 1, 1. So in AND operation, when you have 1, 1, its result is 1, right? So then we need to get the remainder. So when it is, when you're taking the remainder, how do we take the remainder? According to XOR operation. So how do we define the XOR operation? When you have different bits, like 10 or 01, result is 1, right? When you have similar bits, 11 or 00, result is 0, right? For XOR operations. So then 10, it's 1, 01, 1, 10, again 1. So then in order to continue this, we can take this 0 over here and again divide it by 1010. So when you divide it by 1010, answer is 1, right? Because first binary value of the divisor and this remainder is 1, 1. So then AND operation is 1, right? So then when you take the remainder, 0, 0, 0, 1, 1, 0, 1, 0, 1. Again, you can take the 0, 1, 0, 1, 0. Taking the remainder 0, 0, 1, 1, 0, 0, 0. Right? Now what will happen? This remainder's first bit is 0, device's first bit is 1. So when you have 0, 1 in AND operation, result is 0. Right? So when you get the remainder, now we can't use this divisor. I told you that we have to make this into zeros. Now when you get the remainder, it's 1, 0, 1, 0, 0, 0, 1, 0, 1. So now divide 1, 0, 1, 1 by 1, 0, 1, 0. Answer is 1. 1, 0, 1, 0. So 1, 0, result is 1. 1, 1, result is 0. 0, 0, result is 0. So we have to continue this because we are calculating the FCS, right? So we are continuing this. We need to add zeros to the end. How do we add? How many zeros we can add? We can add 3 zeros because the device size is 4. It has 4 bits. So we are adding 3 zeros to the end. So continuing the calculation. 0, 0, 1, 0 divided by 1, 0, 1, 0. Again, the result is 0. And this makes into all zeros. 0, 1, 0. Again, when you divide 0, 1, 0, 0 by this divisor, answer is 0. 0, 0, 0, 0. Taking the remainder 0, 0, 1. Last one. 1, 0, 0, 0 divided by 1, 0, 1, 0. Result is 1. Then 1, 0, 1, 0. We get a remainder. Remainder is 0, 1, 0. And this remainder is the FCS. This is the FCS. So this is the answer for the first question of part C. Okay. So then you'll see what is the next question. In part C, question number 2, the receiver gets the bit stream as 110, 110, 11010 when the device is 1010 and the same frame is requested from this transmit end. Justify the statement by calculating the remainder. Now this is a statement. Statement says receiver will receive this bit stream including the FCS. Include the FCS. This is what the receiver receives. So in this received message, remember we have the message plus the FCS. How do we find how many bits are there for the FCS? If the device size is 4 bits, FCS size is 3 bits, right? So then last 3 bits are FCS, right? Now if you take this bit pattern, this is the FCS, right? So this includes the message and the FCS, and we have the same device like in the previous question, 1010. But the problem is same frame is requested from the transmitter. So that means you are requesting frame from the transmitter to resend it. So you need to justify this statement. Why do we need to ask for resend? So if you are asking for a resend, that means there should be an error, right? That's the reason. So you have to prove it in the calculation. That's what you have to do. Right? So this is the bit stream that we are receiving. It's 110, 110, 110, 10. And the device is 1010. So as you know, this is the FCS. Okay, we'll do the calculation quickly. So this is the remainder. Now this time, this is not the FCS, right? This is the FCS, right? And this is the remainder. So actually this calculation was done to the receiver's endpoint. So receiver receives this message, including the FCS, and we have to calculate the remainder. So the statement says that you have to ask for the same frame again from the transmitter's endpoint. So you can see what is the reason. Remainder contains ones, right? The remainder is 100. So there's ones in the remainder. So then the data that you received at the receiver's point is containing some errors, right? So therefore, the receiver requests the same frame from the transmitter end, right? So you have to write complete answer for that. Okay. Now, calculation is not enough. We need to write the justification as well, right? Okay, so that is the final answer for this question. So when you do the calculation, you have to finalize the answer as well in the statement. Then we have question from question number 3. It's actually, we have ARQ questions and sliding window mechanism. So you need to draw the diagrams of ARQ and sliding window mechanism. First one is based on idle ARQ. A link has been established between two computers that use idle ARQ to send frames. PC A needs to send 3 frames with an equal frame size to PC B correctly. The frame number 3 received at PC B has an error at the first attempt. So we are sending 3 frames from PC A to PC B, and the third one will fail during the first attempt of transmission. So you have to represent this using idle ARQ method. So in this idle ARQ method, we are transmitting frames in between PC A and PC B. So we are sending 3 frames. The special thing with idle ARQ is we will not send the next frame until we get the acknowledgement. So when you send frame number 1, we are not sending the second frame at once. We are waiting till we get acknowledgement from the recipients. So when you receive acknowledgement 1, we can send next frame, frame number 2. And waiting for acknowledgement 2 and sending frame number 3. But for frame number 3, we are receiving negative acknowledgement or error. So then we can't send the next frame. You have to resend frame number 3 and receive acknowledgement for this. So this is the answer for question number part D, question number 1. Okay, so next question. Part D, question number 2. Illustrate the flow control using sliding window mechanism. Assume that there are 6 frames to be sent and frame number 3 had failed during time slot T3. An acknowledgement has been received during time slot T5. The transmitter buffer size is 3 frames. So you need to represent this scenario in sliding window mechanism, right? Altogether, we are sending 6 frames. And as you can see, number 3 will fail during time slot T3. Acknowledgement 3 will be received at time slot T5. And size of the transmitter buffer is, at a time, it can handle only 3 frames. So as the part 3 of the same question part B, you need to draw the timing diagram for this scenario using go back n method, go back n ARQ method, right? So I'm going to do both together, right? Okay, so at a time we can send only 3 frames, right? So if I summarize the question, we altogether we have to send 6 frames, okay? And frame 3 failed at T3 and acknowledgement 3 received at T5. Frame size, buffer size is 3, right? So at a time we can handle 3 frames. So during the first time slot, we can send 3 frames together, right? And then at time slot T3, we can see there's a failure. So we are receiving negative acknowledgement at this time. Okay. And acknowledgement for this frame number 3 will receive that time slot T5. So these two are the most important parts. So if you receive negative acknowledgement as T3, you need to receive acknowledgement 1 and 2 during T slot, time 2 slot, right? So when you receive acknowledgements for frame number 1 and 2, you can discard them and send new frames to the receiver side. Okay. So here I'm sending 3 frames at once, then receiving acknowledgements of acknowledgement 1 and 2, discarding them and sending frame number 4. So in this place, you can send frame number 5 as well. It's not compulsory to send frame number 5 at T3. Even you can send frame number 5 from here. Then T3, during this time, negative acknowledgement 3 will be received. So we can't discard this, right? But we have more space in the buffer. So therefore, I can send frame number 5. So I'm receiving acknowledgement 3 during T5 slot, right? So therefore, during this time period, I'm not receiving any acknowledgement. So I need to suspend the transmission. So that's again an important point. So once I receive the acknowledgement 3 at T5 slot, I can discard frame number 3 and transmit frame number 6. So as I told you, we are sending altogether 6 frames. You can see by the time of receiving acknowledgement 3 at T5 slot, I'm sending all 6 frames, right? So now we have to represent this with go back in method, right? So go back in method, we have two PCs, transmitter and the receivers. There we have the transmitter and the receiver. Go back in method also, it's a continuous ARQ method like selective method. So we can send several frames together, right? So at a time we can send frame number 1, frame number 2, because the buffer can handle 3 frames at a time. So we can send 3 frames continuously. Then we have to receive acknowledgements for the sent frames. So then we are receiving acknowledgements for the frames that we have sent. Okay, so by the time that you have sent this, you can see we have more space, right? When you receive acknowledgement 1, definitely it will discard frame number 1. So you have more space in the buffer. So you can send frame number 4 as well, right? So I'm sending frame number 4. So when you receive acknowledgement 2, then we are receiving negative acknowledgement for frame number 3. So when you receive negative acknowledgement, you can't proceed with the transmission. That means you can't send frame number 5. But if you have already sent it, that's okay, right? You can send it, right? Before you receive negative acknowledgement, we can send frame number 5 as well. But once you receive negative acknowledgement, now you can't send frame number 6. You have to correct this one and do the next necessary steps, right? So first thing is like I'm receiving negative acknowledgement. So I need to resend frame number 3. So once you send frame number 3, if you are using go back n method, what's next? Can we continue or do we need to restart? Can we continue this or do we need to restart? We need to restart. Very good. We need to restart. So by the time when you send frame number 3 and by the time when you receive acknowledgement, negative acknowledgement 3, we have already sent frame number 4 and 5, right? But this is go back n method. So if you had to send a failed frame again, you need to restart the process where you have stopped, right? So frame number 3 was resent. So now these frame number 4 and 5 are not usable. So you have to resend them. Frame number 4, frame number 5, and to complete the process, you have to send frame number 6 as well, right? So if you are sending frame number 6, you need to receive an acknowledgement, right? Otherwise, we can't send it further. So we should receive, for this frame, we must receive an acknowledgement 3. So that is the representation of go back n method for this same scenario. So now you may have a doubt why we have a huge gap between Act 3 and Act 3, right? Negative acknowledgement 3 and acknowledgement 3. So can you see there's no acknowledgement received during this time slot, right? So there's a suspended time period. So this time period is the suspended time period. Okay, so next we have question number 4. Question 4 is based on lab questions as well as wide area network questions. So we'll start with the first question in question number 4. Question number 4, why do you need structured cabling? State 3 reasons, right? Why do we use structured cabling? Structured cabling was the 6th lab session. It was a assignment to be submitted. So I hope you have submitted your answers to the submission link. So in the structured cabling method, that's how we actually network in an organization network, right? When you're handling physical network in organization, we need to have plan for it. And we are calculating what are the devices, what are the cables that we need to purchase before you implement it actually, because implementation of a new network for an organization will be very high cost process, right? So you have to manage it properly with especially managing all the resources properly, because these resources like routers, networking devices, like routers, switches, and all of these devices and cables are very expensive things. So we can't purchase them and then say that we don't need them, right? So before you design the network, before you implement the network, you need to design it, right? So that's what we do with structured cabling. So why do we use structured cabling? These are the reasons. In the slides also I have mentioned, these are the reasons. Time saving, if you have properly maintained structured cabling environment, it saves your time because you can easily troubleshoot, right? You can identify where you have faults, and also if you want to make new connections, it's easy to identify and manageable, right? So it's time saving. downtime can be reduced, and if you have a proper structure, even with your environment also, you can see if it is well organized environment, it's manageable, right? So manageability is another benefit. Consistency, right? So when you consider the data transmission, we are expecting very reliable data transmission, right? No failures should occur and no downtime is expected. So we can maintain consistency if you have structured cabling, a proper structured cabling. And this is supportive with multiple vendor equipment. So you don't need to buy devices and cables from one manufacturer. You can go for several manufacturers or several vendors products. Simplify, move in and add in changes, right? If you want to add more computers, add in new devices like networking devices, it will be very easy. And as I told you, it's easy to troubleshoot and can be used in future. So those are the reasons to use structured cabling method. Then the second question, part B question, is based on demarcation point. So demarcation point is the margin, or that is the point where you meet service providers network and customers network. Both networks meets together at demarcation point. So this question is asking what is meant by demarcation point. The service provider is responsible for everything from demarc to the service provider's facility. What is meant by demarcation point? So demarcation point is actually providing you, this will provide you an interface. It's like an interface between network and service provider network. So demarcation point, exactly the meaning of demarcation point is, this provides the point at which outdoor cabling interfaces with the intra-building backbone cabling. So intra-building backbone cabling means that is the customer's network, right? You don't need to use exactly the same wordings. This intra-network, intra-building backbone cabling means that is the customer premises network. Right? So outdoor cabling interfaces means service providers network. So this is the point where we meet service provider network with the customer's network. It represents boundary between the service provider's responsibility and that of the customer. Everything from into the building, it's customer's responsibility. So in the morning also, I told you that the things after the demarcation point, towards the customer side, it belongs to customer's premises or customer premises equipment, and its maintenance part is maintained by customer itself. So it's their responsibility. So there's a question asking whether we get the same format. Yes, you'll be getting same format as I told you in the very beginning of the revision discussion. Part C. Part C is about structured cabling testing, right? Part C question is based on structured cabling testing. A structured cabling system is a complete system of cabling and associated hardware which provides a comprehensive telecommunications infrastructure. So in here, these telecommunication infrastructures usually, like when you implement it, you have to test it. Now with software implementations also, we know that when you implement the application, finally you have to test it. You have to test the system. Before you publish it to the customers, you need to test the application that you have developed. So in telecommunication infrastructures also same, you have to test it before you hand it over to the customer. So this testing method is known as structured cabling test. So what is meant by structured cabling test? That's the question, right? So testing is a major significance for the correct functionality of structured cabling. So if you find problems in the structured cabling system, you can correct it before you hand it over to the customer, right? So we are using special testing devices and special mechanisms to find out what are the problems in our telecommunication infrastructure, right? So this will be done from the customer's endpoint, right? This is not going to be handled by the service provider. So this structured cabling network implements within a customer premises, right? So it will be tested and manageable from the customer's point of view, right? So then we have to differentiate near end crosstalk method and far end crosstalk method. So there we are going to calculate the crosstalk. In twisted pair cables, we can calculate the crosstalk. So near end crosstalk or next near end crosstalk method will calculate the crosstalk in the near end of the cable, comparing the crosstalk between two pairs. Right here, pair number 1 and pair number 2, we are comparing the crosstalk between these two pairs, right? So both pairs in the same endpoint. Far end crosstalk, we will calculate the crosstalk in two different endpoints, right? So we are taking one pair from each side and compare the crosstalk from two endpoints. So in part D of this question paper, it is asking you to explain why wireless networking is required in local area network. So you can give reasons why we use wireless local area networks or WLANs in our networks. So basically, we can provide mobility to our network, right? So when you have wireless networks, installation of wireless network is not difficult like physical network. Okay, so we can have wireless access points and connect several devices together rather than wasting time on physical network. Because in physical network, when we connect devices in a physical network, you have to pay more attention. You need to plan for it properly, because when you're purchasing cables, devices, you need to plan for it, right? And you need to design it before you actually implement it, right? Then only we can get an idea about how many devices we need, how many cables we need, like this. So wireless networking method, we can simply install an access point and connect several devices together. So we can provide mobility to these devices and to the network, right? So easily we can move into a different location, right? In wired network, we can't move into different locations easily. Let's say that if you're moving into a different premises, you can easily restart your work with wireless network rather than installation of wired network or physical connectivity. Physical connections or physical network takes more time to install it, right? So it's, again, we can reduce the time that taken to implement a wireless network. And from anywhere you can work, right? And also we can increase the number of users where they can join into this network, right? If you're adding very good quality access points, you can accommodate many users at once. So it will increase the scalability. And also when these users leave the network, new users can join into the network, right? So let's say that if the access point is supportive for 25 users at time, and if one of these users disconnecting from the network, a new user can be added to the wireless network. So it's increased the scalability, and troubleshooting is also good because you don't need to manage a cable networking here. So no failures in the cables. The only thing is you have to look after the access points. Right? So those are the reasons to move into wireless networks. So the last one is about comparing circuit switching method and packet switching method. So in the morning also we discuss about circuit switching and packet switching methods. In circuit switching method, the resources need to be reserved during the setup phase. So when you are establishing a circuit between two endpoints, two telephone connections, in a telephone conversation, you saw that we have to define the path, right? That path is reserved for that connection throughout the data transmission, right? Throughout the communication between these two users. So it is reserved, but other users cannot use this same circuit during that conversation, right? So the resources are reserved during the setup phase. The resources remain dedicated for the entire duration of the data transfer until the tear down phase. So until these users are terminating the connection, it will last for the whole time, right? This circuit will last for duration during the data communication time. But when you compare the packet switching methods, this will create according to on-demand basis, right? So always on status, right? So this packet switching method, these paths are not reserved, right? So we don't have a dedicated path, but we have virtual circuits which defines path in between sender and the receiver. So you can use these virtual circuits to do data transmission, but these things are not reserved during the data transmission. Circuit switching method, it's a dedicated transmission path, but packet switching method, no dedicated path. And circuit switching method, it will continuously transmit data. In packet switching method, we are transmitting packets. Information will pass as packets. So what are the examples for circuit switching method? Can you give me example networks, technologies, WAN technologies for circuit switching? Technology examples for circuit switching method? Circuit switching method used with PSTN networks and ISDN networks, right? Packet switching method used with frame relay, X.25, ATM, right? So those are the examples of packet switching and circuit switching, right? So that's the end of the final paper discussion. As I told you, there will be a paper based on the same format for your final examination this time as well. So there will be 4 questions. Each question will have 25 marks. So in total, 100 marks will be contributed. But your overall mark, this final paper contributes 50%, right? So you have to work hard for the final exam because final exam paper will be difficult than midterm paper. Because usually the midterm paper will be tested with few concepts, but this one will check with more concepts, and we have covered almost 14 lectures throughout this semester, right? So there are 14 lectures, and including the wide area network, there are 15 lectures, right? And also we have covered some lab sessions. So you need to check what are the lab sessions that you have done, right? So that's all for today. And one more thing regarding the handbooks, you can collect your handbook during the next week, right? So I will hand it over to you. Like you don't need to meet me to collect your handbook, but the marked handbooks, if I have marked them, I will put them into a box in 13th floor, right? Near the reception area, I will keep a box. So then you can collect your corrected handbook from there, right? So when you come on Monday, you can check whether you have, whether I have put handbooks into the box. So if the handbook is there, you can collect it. And if you know your friends as well, you can pass them if you find the handbook as well, right? So during the next week time period, you can collect it. The final exam will start from 17th May onwards, right? Still, I didn't get the timetable of this final examination. So 17th onwards, it will be started, right? I think it will go for 2 weeks time period. Okay, so that's all for today. Thank you for joining this 2 sessions, and I wish you all the best for your final examinations and for your future. Okay, you're welcome. I'm going to end the session.